Okay, well, good evening, ladies and gentlemen, and welcome to this lecture organised by the Manchester Network of the Institution of Engineering and Technology, the IET. My name is Pete Hicks. I'm the secretary of the network, and I'm also chair of its retired member section at the moment. And it's my pleasure to welcome Professor Steve Furber to talk to us this evening about his work on the field of artificial intelligence and the role that he's playing in the Human Brain Project. Many of you will know that Steve is the ICL Professor of Computer Science in the School of Computer Engineering. Computer Engineering, get the engineering in there. In the School of Computer Science here at Manchester University. And he's well known for the work that he did while at Acorn Computers, particularly for pioneering work on the BBC Micro and the 32-bit ARM RISC microprocessor. His research interests at the moment include asynchronous logic design and biologically inspired novel computing architectures. Steve is a fellow of the IET and a chartered engineer. He's also a fellow of the IEEE and a fellow and trustee of the British Computer Society. Steve is a fellow of the Royal Academy of Engineering, and he was elected as a fellow of the Royal Society in 2009 and was appointed CBE in 2008. And that is just some of the many honours that have been bestowed on him. But as I say, it's our pleasure for us to welcome Steve tonight to talk to us about his work on AI and the Human Brain Project. So without further ado, I'll invite Steve to give us his talk.
Thank you very much for that introduction, Peter. Welcome, ladies and gentlemen. Who's doing what wrong? Is that me? Am I shuffling around? Oh, it stopped. Okay. Well, I'm going to talk about SpiNNaker and the Human Brain Project. The first slide acknowledges the sponsors of my research and the various partners. The SpiNNaker project itself has largely been funded by the UK Engineering and Physical Sciences Research Council, but now ongoing use of the platform is funded by the European Union, at least until next week, through the European Research Council and the Human Brain Project, about which I'll be saying a little bit later. The project is about trying to use computers to understand this thing we all carry around inside our heads, which remains as one of the great mysteries of science. We really don't understand the information processing principles at work in the human brain. The topic has been of interest for quite a long time. Last year I was asked to give the British Computer Society Lovelace lecture, so I did a little bit of homework on Ada Lovelace herself, and it was pointed out to me that in her notes she has these words about understanding the brain, that she had hopes of one day getting cerebral phenomena such that I can put them into mathematical equations. In short, a law or laws for the mutual actions of the molecules of brain. I hope to bequeath to the generations the calculus of the nervous system. Now, that was a fairly high ambition for 200 years ago. Sadly, Ada died quite young at the age of 36 and never got to achieve on this ambition. Had she lived a little bit longer and done it, it would have saved a lot of us a lot of time since. Although perhaps even the basics were not in place to begin on this agenda 200 years ago. What I'm going to talk about this evening is indicated in this outline. I'm going to look back a little bit at where we've come from in the world of computing, and then talk about the topic of building brains, understanding brains by trying to construct systems that operate in a similar way to the extent that we understand enough about the brain to define similar. And then onto the SpiNNaker project itself. SpiNNaker is a contraction of spiking neural network architecture. It's a machine specifically designed to support models of the brain. The key innovation in SpiNNaker is how we can model the very high degree of connectivity that we find in the brain. So I'll explain what the key ideas there are and tell you where we're up to in building machines. I'm going to then talk about a little project I've done myself recently on using SpiNNaker to solve Sudoku puzzles, because that kind of illustrates the sort of thing you can do with this technology, and then say where we're going. So, to start at the beginning, well, I've started with Ada slightly more recently. Do we know which microphone is making noises off? Is this disturbing the audience? I can try living without this mic if that helps.
There's a bad connection on it.
I think it's not. Let's just dump that.
That should work.
Yeah. It was disturbing me, even if it wasn't disturbing you. So I hope we'll have a slightly cleaner audio now. So I live 10 miles south. I commute into town on the train most days when I'm here, and about 1.5 miles from where I live, which is in Wilmslow near the airport. The other side of Wilmslow, there's this house, which is a rather inconspicuous semi-detached house set back from Adlington Road that has the blue plaque over the brick arch you can see to the left, and the plaque talks about Alan Turing as the founder of computer science and cryptographer, whose work was key to breaking the wartime Enigma codes. And in this house he lived and indeed died while he was up in Manchester. And while he was in Manchester, Turing worked on a number of interesting topics. He spent quite a lot of time working on morphogenesis, which is how cells break symmetry. We all start as a single cell which divides, and then those divide and so on. At some point, these cells have to break symmetry. They have to differentiate. Some have to become brain cells, some skin cells, and so on. And Turing was very interested in the mathematics of that symmetry breaking process. But while he was here, he also wrote a paper which has become seen as seminal, which is the one shown on this slide. It's a paper entitled Computing Machinery and Intelligence. And the paper begins with the words, "I propose to consider the question, can machines think?" Now this was published in 1950, just 2 years after the world's first stored program computer ran its first program on June the 21st, 1948. So this is very early in the history of computing. Turing is already beginning to think about where this technology might go in the future. And in this paper, he decides that this opening question is not well defined as a research question, so he turns it around into what he called the imitation game, which of course is the title picked up by Hollywood for a movie about his life recently. But the imitation game is known to everybody else simply as the Turing test for artificial intelligence. And it describes a protocol for determining if machines have achieved human levels of intelligence. Now, Turing thought that all that was required to improve the Manchester baby to pass his test was more memory. And he predicted that by the end of the 20th century, computers might have a gigabyte of memory. That was a remarkably accurate prediction when you think about this. The Manchester baby started off with 128 bytes, and then that was doubled after a little while. But it's still quite a big prediction, and it was about the turn of the century when a typical PC in your home might have had about a gigabyte of main memory. But he thought that's all it would require. The Manchester baby was quite fast enough. If it had more memory, it could then be programmed to pass his test. Now, at the turn of the century, machines were 1 million times faster than the baby, and they had a gigabyte of memory. But still, even today, quite a long time after the turn of the century, no machine has convincingly passed Turing's test. And he would have been very surprised about that. I know there's a little bit of controversy because the test was run, I think, last year or the year before at the Royal Society, and a machine kind of fooled a number of the judges a bit, but it cheated. really? Well, the consensus is, it pretended to be a young Ukrainian from a village in the Ukraine that nobody on the panel had ever heard of, which made it a bit difficult for them to ask questions about its upbringing and so on. So the general consensus is that no machine has yet convincingly passed Turing's test. And my take on this is that the reason we found artificial intelligence, in the general sense of artificial intelligence, much harder than Turing and many people since him have anticipated, is because we've never actually worked out what natural intelligence is. This thing that our brain does that gives us what we call intelligence is not understood. And so we don't really know what it is we're trying to model in artificial intelligence systems. And that's really why my research over the last 20 years has come back to looking at using computers to try and accelerate our understanding of the brain as a precursor to working out how to make machines more intelligent. Now, Turing came to Manchester because Manchester had the first operational machine that implemented his big theoretical idea from the 1930s of the universal computing machine. And it's shown here with its two principal designers, Freddie Williams and Tom Kilburn. At the university, we've been building machines ever since. And there's a history of machines that I don't have time to go into. The most recent one, which I will be talking more about, is SpiNNaker. And SpiNNaker has quite a lot of computers built inside it. And it's typical, for the purposes of this point of the talk, of just a modern, reasonably energy efficient computer. And if we compare those two machines, then we can see how computing has moved forward in the 63 years that separates them. So the baby machine used about 3.5 kilowatts of electrical power, and with that it would execute some 700 instructions a second. If you do the sums, you can see that means it used about 5 joules for each instruction. A modern processor, such as the one we use on SpiNNaker, this one uses 40 milliwatts of electrical power, with which it will execute some 200 million instructions a second, and that gives you an energy per instruction with too many zeros after the decimal point to read out. But if you take the ratio of those two numbers, what you find is that computers have improved in their energy efficiency by a factor in the region of 25 billion in just over half a century. This is formidable progress. It's very difficult to understand what these big numbers mean. One analogy I like is I understand that the entire UK road transport fleet, all the cars, buses and lorries in the country, between them use about 50 billion litres of fuel a year. And hence we have giant oil fields and big super tankers moving all this fuel around just to keep the country moving. So had cars improved their fuel efficiency by the same factor as computers over the last half century, we'd be able to run the whole country off about that much fuel. Okay, that would keep all the cars, buses and lorries running for a year. Now, I'm enough of an engineer to know that there are good sort of theoretic fundamental reasons why it's harder to improve the energy efficiency of cars than it is to improve computers. I'm still a bit surprised the car industry has only really started trying in the last 5 years, but that's a different story. The point is just to emphasise how big this number is, and this is one of the reasons, along with cost, why computers have become so pervasive. There's a famous quote of a leader of IBM who predicted that 5 computers would be enough for the world forever, and the company I deal with, ARM, about 6 months ago announced the 75 billionth ARM shipment. Okay, so there are now 10 ARM processors for every human on the planet. And the reason there are 75 billion and not 5 is partly because they're so much more energy efficient. Of course, it's also partly because they cost a lot less than they used to. So we've seen huge progress. Now, the counter to this, of course, is that computers are using an increasing proportion of the world's energy supply. So they're getting much more efficient, but cumulatively they're using more resources. Why is this? And it was pointed out to me, this is an example of what is known to the economists of Jevons paradox. in the mid-19th century, Jevons, who was at Manchester University, published a book called The Coal Question. And in this book, he pointed out that steam engines were getting much more efficient, and so you might expect that the coal consumption overall would go down. But what he observed was the opposite. Coal consumption was going up, despite James Watt's improvements in efficiency over Thomas Newcomen. And when you think about this, the reason is obvious. Okay, as you improve the efficiency of a piece of technology, the number of uses to which you can put it grows even faster than the efficiency. And so the product of the number of products multiplied by their efficiency goes up rather than down. This leaves engineers in a bit of a dilemma. It says the more efficient you make something, the more damage it does to the environment. I don't know how to resolve that, but it's a challenge. One thing I would say is that the picture at the bottom here is Manchester in the mid-19th century. I think it's improved a little bit in terms of pollution since then, which is good for all of us. So, where have we got to in this process with computers? And this leads me to the two major research questions that motivate the SpiNNaker project. Computers have advanced formidably over the last half century, and we now have really formidable computing resources available very economically. Can we use these resources to accelerate our understanding of the brain? Understanding the brain is difficult. The neuroscientists start at the bottom and probe individual neurons, and then 10 neurons and hundreds, and they're approaching thousands being able to probe at one time. They work bottom up. But psychologists, on the other hand, tend to work top down. They look at behaviour and look at movement and activity in the brain. But all the interesting information processing happens at intermediate scales that you can't reach from either end. Okay, you can't find them top down, you can't get to them bottom up with current technology. And therefore the only instruments we have available to understand what's happening at these intermediate scales are computer models. Feeding the biological data into models and seeing if we can replicate aspects of brain function. And there's formidable computing resources available to do it. They're not quite formidable enough for some purposes. The best estimates of the amount of computing power it would take to model a whole human brain still exceed exascale, 10 to the 18 operations per second. And the world of high-performance computing is still struggling to work out how to build exascale machines. So we can't yet build machines capable of supporting whole brain models at the human scale. But we can get quite a long way towards that, and of course that progress in high-performance computing is rapid and continuing. And the second research question is, as we do learn more about the brain, can we use that to work out how to build better computers, where better might mean more efficient, might mean more parallel, because we've no choice in computing now but to go parallel, understanding fault tolerance better, and so on. So these are the two research questions that guide the work that I'm going to talk about. Brains. What do we know about brains? Well, we know that they're massively parallel. The world of computing has had to embrace parallelism, but it's still fundamentally a major challenge to build efficient parallel computing systems. The brain solved this problem millennia ago. We each have just under 10 to the 11 neurons, 100 billion neurons inside each of our heads, all operating at the same time, and they are connected through 10 to the 15 synapses. That's a junction that connects an impulse from one neuron to another. And one of the strange things to think about here is that your entire personality and all your memories are somehow captured in the way your synapses have formed initially through your DNA and then subsequently through your life experiences. Essentially, your synapses are you to a considerable degree. The brain is impressively power efficient. I said we need exascale computing to build whole brain models at human scale, and the high performance computing industry is struggling to get exascale down to what they consider is the maximum economic power consumption, around 20 megawatts. Your brain operates on about 20-25 watts, so you're something like 1 million times more power efficient. And of course that's one of the answers to the to the warnings we hear about existential threats from AI. If we could build a computer that could model the human brain, it would occupy a large aircraft hangar and use 20 megawatts, and it's just not competitive as a way of controlling something compared with biology, and it won't be for a very long time. I think the key to the brain's power efficiency is in the next two bullets. The brain's made of relatively slow stuff, so nothing inside your head operates on timescales much shorter than about a millisecond, whereas this computer, the designers worry about things on timescales of picoseconds. So there's a big scale difference there. And similarly, the communication inside your head runs at a few meters a second, whereas chip designers get frustrated by speed of light limitations and number of clock cycles to get across a centimetre of silicon. Biology is much more relaxed about raw speed. And I think there's something for computer designers to learn here. If you're challenged as a computer engineer with designing a fast computer, you start off finding the fastest components you can find, and then you build them into the fastest sequential engine you can design, and then when all else fails you go parallel, because that's the bit we don't understand. Biology's got a very different approach. It uses modest performance, and we know that pushing performance up in computers means sacrificing energy efficiency. We haven't thought very much about what going in the other direction might mean, of deliberately sacrificing performance to gain significantly improved energy efficiency, and then exploiting parallelism to get overall performance. That's not a very thoroughly explored area of computer architecture. The brain's also very good at coping with component failure. As you sit here listening to me, you're losing about 1 neuron a second. That's the average loss rate through the adult life of the human brain. Don't panic. It only amounts to 1 or 2% over the total useful life of your brain, and your brain can cope with 1 or 2% component failure quite comfortably. If you start losing 20 or 30%, you have a problem. But 1 or 2% normal failure rate is fine. Whereas with a computer, I have several million transistors which are mission critical for this talk. If any one of them fails, the screen will go blank and I'll have to make the rest up from memory. We really don't know how to build computers that will cope with 1 or 2% component failure. That's something we can learn from biology. And of course, brains learn in interesting ways. They don't have to be programmed in detail, although we spend a considerable amount of gross domestic product training brains. That training is at a much higher level than writing low-level code for each individual. So there are things we can learn from brains. What can we say about how they work? Well, I've mentioned neurons. These are the basic brain cells, and to a considerable degree you can view neurons as a bit like logic gates. They're multiple input, single output devices. They sense a whole lot of different inputs, and when some pattern arises that they're interested in, they generate outputs. They tend to have many more inputs than logic gates. Chip designers typically use gates with 2, 3 or 4 inputs. The neurons in your brain have 1,000, 10,000, occasionally hundreds of thousands of inputs. So there's a bit of a difference there. But fundamentally, if you think of them as multiple input, single output devices, then there's something you can get to grips with. And of course, they're highly scalable. So some animals, C. elegans gets by very nicely with 302 neurons to control itself, and it survives very well in the modern world with its 302 neurons. We have 10 to the 11, and you can find everything in between. So as with logic gates, if you have a few, you can build a simple state machine. If you have a few billion, you can build a supercomputer. Its scalability applies. And the neuron is pretty similar right across the biological scale. There is structure in the brain. It's not just a random mess of cells squished together. the neuroscientists can draw things which they call microarchitectures, borrowing words from computers. And the drawing on the bottom right here is from Alex Thompson at UCL, and that's the 6-layer cortical microarchitecture. It looks like a circuit schematic at first sight, until you go and look closely, when you find that all the detail you need to make one is actually missing, because it's not known. But there's regularity in structure there, and one of the things that fascinates me is that the cortex, which is the outer layer of the brain that's kind of screwed up and fitted around the older inner bits of brain inside your skull, that is pretty similar at the back of the head, where it's doing things we sort of understand, low-level image processing, edge detection and so on, in what you see with your eyes. And at the front of the head, where it's doing things we have no idea about, such as higher-level thinking and natural language processing. The fact that the physical structure is very similar suggests strongly to me that the algorithms are likely to be quite similar too. Now, we don't know where that leads, but that's one of these are the things that lead me to believe that we do have some starting points in this quest to understand how the brain operates as an information processing system. Now, of course, we're not the only people thinking along these lines. Indeed, the generic class of technology we're working in is called neuromorphic chips, and in 2014 the MIT Technology Review highlighted neuromorphic chips as one of 10 breakthrough technologies to look out for, and they describe it as microprocessors configured more like brains than traditional chips could soon make computers far more astute about what's going on around them. I think that's a fairly optimistic interpretation of where we are in neuromorphic computing, but it shows a degree of interest. And the following year, not to be outdone, the World Economic Forum listed its top 10 emerging technologies of 2015, and in there at number 9 is neuromorphic technology. And interestingly, there's a whole set of other things in their list which are quite closely related. So sense and avoid drones, emergent artificial intelligence, and next generation robotics are all kind of applications that could potentially benefit from neuromorphic technology if we knew how to make it work properly. In terms of building neuromorphic systems, there are some big players. IBM has been developing their neuromorphic technology for about as long as we've been developing SpiNNaker, which is a very long time. We started building 10 years ago. And they've built very advanced silicon chips that you can that have 1 million configurable neurons on them, and these run at formidably low power. They can operate these things at below 70 milliwatts. It's the biggest chip IBM's ever made, and you can scale them up by putting multiple chips together. And they've managed to sell large systems of these to major government labs in the US. Down the road from IBM, who did their True North development at Almaden in San Jose, is Stanford, and there Kwabena Boahan has been leading a group developing the Stanford Neurogrid. This is a set of chips based on neuron models. The IBM chip is all digital. These chips are analog. Indeed, they use a technology first proposed by Carver Mead of sub-threshold analog systems, which means all the transistors are what we digital designers call off, and they simply compute with the leakage currents through these transistors, which gives them very impressive energy efficiency. And they can get about 1 million neurons on this circuit board. Our partners in the Human Brain Project at Heidelberg are also building analog neuromorphics, and they're doing some very ambitious technology work. So they're using wafer scale neuromorphic systems. Instead of splitting the wafer up into lots of small chips, they use the whole wafer as it is, an 8-inch plate-sized disk, and they are building neural circuits which run 10 to the 4 times faster than biology, because their analog circuits are not sub-threshold, they're above threshold. And the difficulty with analog circuits is to make them go as slow as biology. So at Heidelberg they don't, they go faster, and what they will argue is that if you want to model 5 years of childhood development on a real-time neuromorphic system, that will take 5 years, and on their system it'll take 5 hours. So there are arguments for running these systems very fast. There are also arguments for running at real time for applications in robotics and so on. So all of this has come together for us in this European project called the Human Brain Project, which has become politically quite contentious, but is a good environment for the work we've been trying to do. We kind of brought the SpiNNaker platform funded from UK sources. We brought it into the Human Brain Project sort of ready to go. And the Human Brain Project was one of the 2 successful flagship proposals. The other one was graphene, which I think you're hearing about next week. Is that right? So you get 2 flagships in 2 consecutive weeks. Flagships have what I call headline €1 billion budgets. By headline I mean the €1 billion is more apparent than real. What it actually means is the European Commission is putting half that amount in, and the other half is going to magically appear from other sources, in the usual way of these large research projects. And indeed the pro rata funding for the early stages has been much lower than that. It still sounds like quite a lot, 54 million funding over the first 2.5 years, but if you realise that there are 120 universities involved in this, and you divide your 54 million by 120, it then doesn't look like a particularly big budget at all. And it's going to continue for another 7.5 years, assuming we get things signed off under Horizon 2020. Of course, we're reviewed at several points to assess progress. And this was originally put together by Henry Markram at EPFL and Karl-Heinz Meyer, who leads the Heidelberg work. The governance has changed twice quickly since that started. What's the Human Brain Project about? Well, the high-level summary, the first misunderstanding is people think it's a neuroscience project because it's about brains. It's funded under the European Union ICT budget, so it's an ICT project. It's about computer technology. It happens to be about computer technology, in this case, applied to support brain science, but it's not fundamentally about funding neuroscience. It's about providing ICT support for neuroscience and informing ICT from neuroscience. So it's very similar to the SpiNNaker research objectives. The big research areas are doing things for neuroscience, such as neuroinformatics and brain simulation. The key argument here is that in neuroscience there are 100,000 papers published every year on neuroscience. What you don't need is more papers. Okay? What you need is systems that allow you to aggregate the information that's already been generated and make it accessible and usable. And that's being done through neuroinformatics platforms and putting the results into models that can be integrated into brain simulations of various sorts. The story is similar under medicine. One of the big motivations for trying to understand the brain is that diseases of the brain cost the developed economies more than cancer, heart disease and diabetes put together. Okay, so it's a formidably expensive area of medicine. And the big pharma companies have largely stopped investing in drugs for brain diseases. And the reason they've stopped is because the way they develop drugs today is they have models of the disease and they design drugs to attack some point in the linkage to interrupt the development of the disease. For brain diseases, they don't have the models, so there's nowhere to start from. The old empirical way of finding a random tree in the jungle and feeding it to somebody and see if it has any therapeutic effect is too expensive. So big pharma's largely stopped, and one of the hopes is if we can add to the understanding of the brain and develop models they can use, they will resume development of treatments. As I say, brain diseases are formidably expensive. They're also, of course, extremely distressing for the people affected and their families. So it's an important area in medicine. And what the project is doing here, largely, is it's trying to aggregate information. At the moment, these diseases are treated in various hospitals around Europe. And the data, of course, it's personal data, it's all kept very securely within the hospitals. And the project is finding ways to access and find correlations across this data between hospitals. Not by pulling the data out, the data stays in the hospital so it stays secure, but by looking for patterns in it. And then the third major theme is future computing, which is the idea that as we learn more about the brain, we can use that to inform the design of better computers. And that is manifest in two ways inside the project. The first one is the use of brain models and the idea that you want to interact with these. Most high-performance computing work is done as batch jobs. You feed your program and data in, and then you come back the next day and get the results. For a lot of this brain modelling, it needs to be interactive. And the idea of turning a supercomputer in an aircraft hangar into a personal computer that you can interact with in real time is fairly innovative and will push high-performance computing forward across the board. And then the second idea is where we come in neuromorphic computing, which is taking ideas from the brain and feeding those back into the design of computers to see if you can produce machines that will do computations that aren't possible with standard computers, or will do standard computations more efficiently. So that's where we are with the Human Brain Project, and our contribution is rolled up in this thing called SpiNNaker. From the outset, we've had this plan. This plan goes back to 2005, if not earlier, of seeing if we can put 1 million mobile phone processors together in a machine for brain modelling. And the sums make it clear that even from the outset, with 1 million mobile phone processors, you only get to 1% of the scale of the human brain, with lots of assumptions that simplify the problem. So we're a long way off being able to do whole human brain models, but it is equivalent to 10 whole mouse brains, which is another way of looking at it. One of the nice facts is that a mouse brain is roughly 1,000th of a human brain, if you count it. It's very similar in many respects, except it's scaled down by a factor of 1,000, which makes it a bit more tractable. And you might ask, why 1 million? Well, it's a big number, so we had to worry about the scalability of the machine from the outset. And it's also sort of the limit of what you can sensibly plan to do on an academic research budget. Okay, so we've been generously supported by EPSRC, but we are working within academic research constraints, and so 1 million seemed a reasonable limit. And to hit 1 million, we had to build a machine on a budget of £1 per processor. Okay, we had about £1 million for the build, and we've just about hit that, close. Though it's taken a long time. So, sorry, I thought I was showing you that slide. That's what I've been talking to for the last 10 minutes. Slight error of judgment. So the 1 million processors, 10 mice, all stuck into a machine. To build the machine, you have to have principles, and the principles that underpin the SpiNNaker design are listed here. The first one is the brain has many different configurations. The neurons are not randomly connected. The structure, I showed you a picture of the cortical 6-lab microarchitecture. Other brain regions have quite different wiring diagrams, if you like. And we don't want to rewire the machine every time we want to model a different part of the brain. So we virtualize the topology, and we completely decouple the graph which describes the network we're trying to model from the graph which describes the physical machine. And in principle, we can take any graph and map it onto the machine. The second principle is to do with synchronization. Large-scale parallel computers, generally the thing that cripples them is the need to synchronize the computation, and so we don't. The whole machine runs asynchronously. Every processor has its own idea of time. Things happen when they happen, and the processors have to cope, and you have to configure the program so that they can cope. And thirdly, at a more engineering level, this is sort of my long-term principles of computing. Processors are free. The real cost of computing is energy. This is increasingly true for all sorts of computing. And one example is if you buy a PC and you run it, you compute fairly hard for its useful life, you'll find you've spent more on electricity than you spent on the PC in the first place. And that's true pretty much across the scale. The cost of designing an ARM processor into something like a mobile phone is a few cents. So the hardware's essentially free. Unless you buy it from the wrong supplier, of course. You can spend a lot of money on a processor, but then you're buying it from the wrong place. So, sorry, my prejudice is showing. We put these principles together in architecture, which at this level looks fairly conventional. It's a two-dimensional mesh of nodes, and each node, in this case, contains two physical chips. The SpiNNaker chip, which is the processing layer, and a memory chip, which contains the larger data structures. And having built this node, we can then basically tile a two-dimensional world up to almost arbitrary scale with these devices. The chip itself took the first 5 years of the project to design. It's a square centimetre into which about 40 man-years of design effort went. These things are formidably difficult and complex to design these days. The chip, the thing on the right isn't actually a real picture of the chip. None of us in the team have actually seen a SpiNNaker chip. The photo at the top left is from the packaging company who took it in their packaging line. We've only ever seen the packages. And the picture on the right is a graphic that one of my students managed to synthesize from the design data. And we actually put both the chips inside the same package, so that this is the picture on the right is the processing layer. At the top left you can see the lighter coloured square is the processing layer and the darker rectangle is the memory die, which is an industry standard part that's glued on top and then connected up with wire bonding, and the whole assembly is put in the attractive package with the SpiNNaker logo at the bottom left, and we can then assemble these as I'll show you. One key point about the design, this is a picture of the chip showing what the resources are. The chip has 100 million moving parts on it. That's why it takes quite a lot of effort to design, every one of which has to do what it's told. The key to energy efficiency is the processors, shown in light blue on the right, and the memory they work with frequently, shown in green just above the processor. They're as physically close as possible. The energy consumed by a computation is the number of bits of data you have to move multiplied by the distance they move to a reasonable approximation. So the key here is to keep that distance small, and all the frequently used code and data lives within about a millimetre of the processor. The less frequently used data is in the big memory chip, which is accessed through the orange RAM port on the left. That's about 10 millimetres away, following the path it has to take. But the real key to SpiNNaker is the red bit in the middle. When a processor on SpiNNaker models a neuron, neurons communicate by spikes, they emit impulses, and in SpiNNaker we turn each impulse into a packet, which is sent through a packet switch network, like the Ethernet, only scaled right down to keep it small and efficient, because each packet is carrying only about 1 or 2 bits worth of data. And we wrap that up into about a 40-bit packet. And the internet router, which if you look around these buildings, you'll find routers, and they're typically 19 inches wide and about 2 inches high, and they sit in a rack. In SpiNNaker, the functionality of that box is in this 4 square millimetre red bit in the middle of the chip. So we do packet switch routing at the heart of every chip, and that allows us to achieve the degree of connectivity that you find in the brain. And so that's physically how we make it. Logically, how does it work? Well, the key is making the connections, and it's embarrassingly simple, actually. But this is the key innovation in SpiNNaker, is how we connect neurons. Neurons in the brain I said earlier they have 1,000, 10,000, sometimes 100,000 inputs. In electrical engineers terms, that's the fan-in, and of course one of the fundamental results in design is that average fan-in equals average fan-out, and so every neuron connects to 10,000, 100,000 other neurons. And so when it spikes, it emits a packet, but that packet has to then get replicated and find its way to 10,000 to 100,000 destinations around the machine. And the way we do that is we don't tell the packet where it's going. So the processor that emits the spike simply drops a packet into the fabric and says, neuron number 327 just spiked. Okay, that's all the packet says. And then getting that packet to all the destinations it has to go to is the job of the routing fabric. And each of these routers has a table internally where it looks at where the packet has come from, so which neuron spiked, and then in that table it uses an associative lookup to identify where that packet should be sent. So it matches patterns. Each spike is identified by a 32-bit key, and it matches those 32 bits. It's a ternary cam, which means it can have don't cares, so it can look for ones and noughts or don't cares. And when it finds a match, it then goes and looks at the bit vector, and the bit vector simply says which of the local processors, and there are 18 on this chip, which of those 18 it should go to. It can be any subset, it's just a bit vector of 18 bits, and which of the inter-chip links it should be sent out on, and there are 6 of those. So one incoming packet could be up to 24 outgoing packets. 24 is not very useful actually, because that means you're sending it back where it came from, but with excluding that, that allows us to build connectivity graphs that are arbitrary. So the picture on the right, which shows one SpiNNaker board with 48 nodes on, the red square at the bottom left, labelled 1, 1, if you can read that, it's just the lower of the 2 red squares. That's connecting to the 3 adjacent yellow squares up and to the right, and it does that by sending the packet east until it gets to the white square, at which point it goes northeast until it gets to the first yellow square, and then 2 copies are made and it's consumed at all those 3 yellow squares. And we can basically use this to implement arbitrary routing graphs on the machine. There are obviously constraints, but basically it's a highly flexible routing system, and that basically is the essence of SpiNNaker. Everything else is fairly conventional. Now, to use the machine, we don't expect our computational neuroscience collaborators to want to write real-time ARM code, which is what executes on the cores themselves. And so we have a software stack which allows you to describe your network in one of the standard languages. In Europe at the moment, PINE is popular. It stands for Python Neural Networks. It's basically just a high-level description language that you can describe arbitrary neural networks in. And another one is Nengo from the University of Waterloo, who we've done quite a lot of work with. And then the tools will take that description and work out how to allocate the neurons to processors and how to construct the routing tables, and automatically generate the binary image, which you can see in the middle of this picture, and then load that image into the respective parts of the chips themselves to run the model. And that's now all working fairly smoothly. The key execution model, which is another slightly unusual feature of SpiNNaker, is that it's entirely event driven. Again, this is about energy efficiency. The basic state of every processor is off, waiting for something to happen. So all the processors go into a low energy mode, and then when something happens, they wake up, do something, and then go back to sleep. And the key events in neural modelling are the arrival of a packet. Any time a spike can arrive, wake the processor up and cause it to do something. Typically it initiates a transfer of data from that DRAM. It needs the data associated with that spike, and we have what's called a direct memory access, a DMA engine, on each core to do that transfer. And another event is the DMA complete. Processor wakes up and processes the data. And then the third key event is a timer event. time is typically marked by having millisecond ticks. Every millisecond, the processor wakes up, runs the differential equation solver forward a millisecond, and goes back to sleep. And of course, these three events can happen in any order. They can all happen at once. So there's a small real-time operating system to sort it all out and get things to unwind in the right state. So where have we got to with building machines? Well, we're quite advanced now. So the little board on the bottom left is used by quite a lot of our collaborators to develop basic software. That has 4 SpiNNaker packages on and is about the scale you need to model a fairly abstract pond snail brain. Pond snails don't have very big brains, apparently. The big board, which we use for all the larger systems, has 48 packages on, and that will get you up to the scale of a modest insect. Drosophila is fairly easy. Honeybee is a bit too big. It's in that scale. And then these can be assembled in racks, and the one in the middle has got 24 boards in. That gets you to about the scale of a frog brain. And then a 19-inch rack cabinet with 120 boards in has 100,000 ARM cores inside that one cabinet, and that gets you to about the scale of a single mouse. And we've completed building the big machine for the Human Brain project, and one of our students who's lined up a career with the BBC produced a movie to describe how you wire the machine together. So you map the chips onto boards, all of which have to be tested to make sure they work properly, although we can actually accommodate limited 40 components on the boards. And then the boards are wired together with high-speed serial cables, all of which are limited. They can be no longer than a meter, and so you map the machine here. Long cables don't work reliably, and so the machine is sort of folded in one dimension, and then it's folded in the other dimension, and then the set of boards is mapped into the 5 cabinets for the 500,000 core machine, and none of those wires is then longer than a meter. That's about the length limit for the high speeds. We run those cables at 3 gigabits bidirectionally, so they're limited. The guys assembled the machine. If you look carefully, you'll see the machine is telling them where to plug the wires in. And they're all wearing headphones, which are not ear defenders. They're actually getting spoken instructions from a piece of software that's telling them which cable length to get and where to plug it in. So there's the LEDs giving instructions. When a wire is plugged in at both ends, it's automatically tested to make sure it's been put in the right place and is working correctly. And where are we up to? People in my group work very hard, you can see that. So it took the 3 of them 4.5 hours to assemble the 500,000 processor machine. And Jonathan Heathcote produced the video, did the time-lapse photography and edited it into the video, and is off to work for the BBC when he's finished his PhD. So that's the machine without its front doors, and this is the machine which has been put together. Our commitment to the Human Brain project was to have a 500,000 core machine available as an HBP platform, and if you want to use it, you have to join the HBP community, and then you can access it online and submit jobs, which will get scheduled and run. And anybody can do it. It's open to the world now for use. If you can think of something big to run on it, please let me know, because nearly everything that people run on uses about 1% of the machine. So we have to do some work to put some big jobs together.
What about the weather?
Sorry?
What about the weather?
Weather forecasting. That's not really neural network stuff.
Could it be? Could it be?
I don't think so, no. I mean, the machine doesn't have any floating point hardware, so it's not a conventional supercomputer in that sense. You have to do all your computations in fixed point. I don't think the weather people like that. No. Anyway, what kind of thing can you do? Well, this was a little game I played. Is everybody familiar with Sudoku? I've discovered that most of the world knows what Sudoku is, apart from the Chinese. I gave a talk in China last November and nobody in the room had heard of Sudoku. And in fact I had some Chinese visitors from Huawei in Manchester on Monday, and they too had never heard of it. So anyway, this was inspired very much by some work published by Wolfgang Mass and his team at the University of Graz, who are collaborators in HBP, where they built a stochastic computation that solves Sudoku. So I thought I'd have a play at this. In case you don't know what Sudoku is, then the basic rules are that you start with a certain number of these digits filled in, and you have to fill in the rest of the 9x9 grid. And the constraints are that each digit from 1 to 9 should appear exactly once in each row, in each column, and each 3x3 square. So that's a set of constraints. And Sudoku problems come in a range from easy to medium to challenging to diabolical. To model this using a neural network, I basically built populations of neurons that 25 neurons representing each possible digit, so 225 neurons in the cell, a random spike source that generates a Poisson spike train to introduce some noise into the system, so it could solve some of the harder problems, and that gives you a total of 36,500 neurons. So it's a non-trivial network, and the initial values are imposed by just applying a bit more random input into it. And then you set up the Sudoku rules as inhibitory constraints. So if in a particular cell the digit 2 is working hard, then that inhibits the digits 1, 3, 4, 5, and so on. And that requires 3.5 million synapses. And then if a digit in a particular row is a 5, that suppresses 5s in the other cells in the row, and the other cells in the column, and the other cells in the 3x3 square. And that gives you another 9 million synapses. And you can describe the whole thing in Pine in 165 lines of Python. Okay, so it's not hard. I don't do hard programming. I leave the hard programming to the RAs and PhD students. And one of my guys suggested, one way to observe progress is to measure the entropy of the entire network. And so in here we compute the probability of a particular number just by counting the number of spikes in a time window with a bit of smoothing. And the favoured choice is the one that's got the highest probability. And then the entropy of the network is just the sum of minus p log to the base 2p over the entire network standard entropy formula. And if you work it out, the maximum value the entropy can take is when everything's equally likely. That's when there's the minimum information state. And that gives you a maximum entropy of 256.8 bits. And we can see how that behaves. And if you feed it a diabolical Sudoku problem, what you can see on the left is a real-time animation of the solution emerging. The grey cells are the initial conditions, or at least when they're consistent with the rest of the solution. And on the right-hand side, the top graph is the entropy, which is shown red when the most likely solution is wrong and blue when it's right. So you can see the entropy falling from, it starts at about 250 and it falls, and the spike rates are shown in the bottom right. So this network most of the time solves diabolical Sudoku problems in about 5 seconds, which is a lot faster than I can do them. I'm not really a Sudoku enthusiast, so I don't really do them myself, but humans tend to do these very sequentially. You tend to find one square where you've got a fair idea what goes in there, and you fill that in, and that gives you some more clues. So you tend to go sequentially around. This is doing the whole thing in parallel. Effectively, with the stochasticity, it's communicating the probability of a particular digit in a particular cell, and it's.
Does it ever make a mistake?
Oh yeah.
With my experience as Sudoku, if you make one mistake and you don't notice it, you're knackered from then on, because it's whatever you're depending on is wrong.
On these very hard puzzles, about a third or a quarter of the time, it falls into a local minimum. So it finds a non-solution that it can't get out of. So it's not perfect. This is still a work in progress. It's not finished yet. But most of the time, it solves these. There are mysteries about how much noise do you need, and if you were doing simulated annealing, then you'd kind of reduce the noise as the solution emerged. It turns out this behaves weirdly if you do that, but that's too much detail. I'm running out of time, so I'll just talk about what interesting things might happen shortly. Well, the most interesting thing we're working on, I've been saying this for quite a long time, the student who's doing this does keep finding fundamental difficulties, but our collaborators at the University of Waterloo have this model they call SPAWN, which generated a lot of excitement when it appeared in Science a couple of years ago. And SPAWN is basically a sort of multifunctional brain model, and you see it here solving a simple IQ test, working out what should appear in the bottom right square. It's unique in that it's a multi-behavioural network, so you don't change the network, but it will display multiple different behaviours depending on its inputs. It has one eye and one arm. It looks at the inputs and it handwrites the output, and it can do things like copying the style of the writing and so on. It's quite an interesting model. It currently runs on quite a high-end machine, and it takes about 2.5 hours for each second of real time. And on SpiNNaker, when we get this working, which I'm told is real soon now, I've been being told that for quite a long time, it'll use a lot of compute resource. It'll use about 12,000 processor cores, about 15 of our big boards. So it's still quite a small proportion of the big machine, but it will then run in real time, and that will then offer the prospect of replacing the sort of virtual eye by a physical electronic eye, and the virtual arm by a physical arm, and it'll allow features of the model to be scaled up, which they don't want to do at the moment because it's already slow enough. So that's one of the more exciting things we're about to take on. And this is really beginning to build things which, to some extent, appear to function in a similar way to the brain. In other ways, we know that there are ways this model is quite different from a brain. But that's, as people begin to understand how to put these functions together, I think we'll learn a lot. And making them go in real time allows them to be interactive and easier to deal with. So I should wrap up at this point. Just to conclude what I've been saying, SpiNNaker's been 15 years in conception, and 8 years, actually it's more than that, in construction now. But now it's ready, it's out there, anybody can sign up to use it. We have about 90 systems out with groups around the world. I have a map of the world where the SpiNNaker machines are, and we cover every continent apart from South America and Antarctica. I'm not very hopeful about Antarctica. We built the 500,000 core machine, and that's up and running and available for anybody who can think of something useful to do with it. And we're going to expand that to our original goal of 1 million, but I carefully did not commit to the Human Brain Project to deliver the 1 million core machine, because I knew there'd be some interesting issues to do with debugging the back end of the board supply. Okay, some of the boards will be quite hard to debug, so we bought ourselves a bit of time on that. We're looking for interesting large models to run, probably neural, but weather forecasting probably isn't a good one, but we are working with people who are interested in using these things for sort of things like finite element analysis and protein folding. I don't know if it's good for that or not. And ongoing support for the machine is supported through the Human Brain Project. We've been doing this for a long time. I've seen several waves of PhD students pass through and move on, so a lot of people have contributed to this in the course of its development. I've got most of their names here. I'm not quite sure if I've forgotten anybody, but as you can see, a lot of work has gone into getting this into the position where we are, but now it's ready for use, and I'm excited to see what uses people can find for it, and we're going to try and find some ourselves as well. And with that, I think I'll stop, and I'm happy to take questions.
Well, thank you very much, Steve. Extremely fascinating talk. I'm now going to have to add an image of 10 mice trying to solve diabolical Sudoku puzzles to the one about the monkeys typing Shakespeare. We have time for some questions. Would anyone like to ask a question of Steve?
Yes. Is it possible for somebody from industry to get their hands on one of the snail grain boards? Or is it
To get their hands on?
one of the snail grain scale boards?
So we're in an interesting position at the moment in that because we've developed the entire thing with academic licenses, we are restricted as to what we can do by way of sales. Now we have renegotiated all the relevant licenses to allow sales to academic research labs, okay? And I am currently in the process of further renegotiation to allow some kind of sales to industry labs and national facilities. We've got interest from the likes of Sandia Labs and Jülich Supercomputer Centre in buying fairly substantial machines, but at the moment we can't sell them. But hopefully that will change soon.
To what extent do you see the neuroscience and medical aspects of the project influencing your work?
The neuroscience influences a lot. We're working quite a lot with computational neuroscientists. So one of the larger models we have running is a model developed at Jülich in Germany, which is a cortical microcolumn model, which is scalable to represent a certain area of cortex. So we're certainly working with neuroscientists. We're some way off being able to make contact with the medical stuff at the moment. Right? We need to get further into functional models before we have anything sensible to offer the medics, I think. That's the sort of 10-year goal, not the early goal. I mean, I have some collaborations with neuroscientists here in Manchester where we're looking at neuroscience models. And one of the challenges with brain models is the whole brain's too hard. We don't know enough, and it's too big. So you take a piece of brain, okay, and now you have a black box where you've got very little idea what's happening inside, not much idea what the inputs look like, and not much idea what the output should look like. Now test it. that kind of problem comes up a lot. So you see models like cortical models where, if in free run the model kind of generates the right sort of waves that are measured with neural probes in sleeping mouse brains, this is deemed a success. But it's quite difficult to actually define an experiment where you know enough to be confident that your model is capturing something significant about the real biology. One of the easy areas is the visual system at the back of the head, because that's one of the best understood, and it has the advantage that the sensory input from the eye is unidirectional. So the stuff that flows from your retina down the optic nerve only goes one way. Almost everywhere else in the brain, if signals go from A to B, they also go from B to A. And separating the forward path from the backward path is very difficult. But the inputs into the early visual processing are quite well defined and have been extensively studied. So we know what kind of characteristics you'd expect to see. I mean, if you look at the orientation selectivity part of V1, you get these classic spiral forms, and if you build a model which, given realistic visual input, generates spiral orientation forms, then you can claim something about capturing something that's known about the biology. But otherwise it's very difficult.
Good question here.
I think that last answer what I was going to ask.
Oh, okay. 2 for 1.
Early on in your talk, Steve, you talked about the trade-off between complexity and speed in real brains. Now, obviously, this machine you've made is using ARM processors because they're what's available. Is anyone thinking about modelling neurons using low-speed technology?
Well, that's what the analog neuromorphic people are doing. Okay, so if you look at the Heidelberg or the Stanford system, in there you'll find a little electronic circuit which represents the internal state and behaviour of a neuron. And essentially, Usually what's happened is the neuroscientists have made measurements. These have been abstracted into mathematical models, differential equations. The differential equation has been mapped into an electronic circuit. There are very good, strong analogies between what happens in the biology in terms of ion channels. So ions move in and out of the neural cell through the membrane. And that process is quite similar to the movement of electrons in transistors. And Carver-Mead made a lot of this analogy, that in some sense the electronic circuit is more than simply solving the equation. It's actually modelling the biological process at some, not exactly, but by analogy.
Is anyone placing any bets on which of these approaches is likely to?
No, the field's wide open. If you compare the two digital big neuromorphic systems, ours with IBM's True North, then what you probably say is that IBM has an eye to applications where they can use this neuromorphic to deliver a useful function, such as front-end vision system for driver assist or something. Whereas we have a system that's actually much more flexible but less dense, and so I see our platform as primarily a research platform. I see SpiNNaker as a kind of FPGA for neurons. When you've worked out what it is you want, you can probably go and implement it much more efficiently. But if you don't know what you want, having a platform that's very flexible is a good way to find out what you want. And IBM's chip, the synapses are basically binary with a bit of global weight modulation, and the binary nature of the synapse means you can't implement learning on it. Right. So basically True North can't support learning directly, and learning is viewed as pretty key by most of the biologists.
Yes, please.
How far away do you think you are from having a machine that would become self-aware? Well,
no idea. I don't know how to ask the question sensibly. Clearly at the sort of far end of AI, there are all these deep questions about what is consciousness, what is self-awareness, how is it supported? I think if you ask most neuroscientists, they would tell you it's probably an emergent property of a complex system of neurons, pretty much as we understand them. Of course, if you ask Roger Penrose, he'll tell you that can't be true. Okay, Penrose wrote the book called The Emperor's New Mind, which is a critique of kind of stuff, at least the kind of stuff we're trying to do if you think it extends all the way up to awareness. We wouldn't make that claim because we don't know what that means, but he would claim you have to resort to some other explanation because anything that's restricted to the Turing universal model can't possibly be conscious, right? And the book presents a proof which most people I talk to don't believe. So it's an area of controversy, but it's a kind of, at the moment, a bit irrelevant because the kind of problems we're trying to solve are much more basic than issues of consciousness. I mean, if you force me to guess, I would probably be on the neuroscientist side that a sufficiently accurate, sufficiently complex system will begin to display consciousness. But I don't know that. It's my best guess. I mean, one of the interesting things to think about with consciousness is where it's not binary, okay? I think I'm not a dog owner, but I think most dog owners would claim their dog is conscious. But perhaps its consciousness is a bit more restricted in time and space than the human. Okay, so what about a mouse? Probably. An ant? I look at flies banging their head against my conservatory window repeatedly. I think this could just be an autonomous robot following a set of rather stupid instructions.
Something like a fly, sort of order of neurons and synapses and all the rest of it, would that insect have?
Sorry, what?
With something like a fly, an insect.
Yeah.
What sort of order of numbers of
Well,
neurons?
Drosophila is about 100,000 neurons.
100,000.
Probably about 100 million synapses. It's a lot for that tiny space. And you can kind of... So the insect people we talk to, and there are quite a lot of people who study insect brains because they're smaller and therefore, in principle, simpler, although some ways they operate make life difficult. So mammalian brains principally communicate with spikes, not entirely, but there's far more analog communication going on as you go down the scale. But the bee people will tell you the bee is the simplest brain that has interesting cognitive capabilities. So you can train a bee in a lab to follow a colour. Okay? Train it with rewards and it'll go the blue way rather than the green way or something. And you can't train Drosophila to do that. So maybe there's the critical point. But does that make a bee aware? I'm not sure. Is a bee aware of what it's doing? I mean, these are very hard... I don't know if I should say this, but I mean, I guess everybody's gone through this process when you're sort of in childhood. You actually wonder if you're the only conscious person around and everybody else is just a robot. or is it just me? I don't know. I think this is not an uncommon childhood sort of thought. But as we become adults, we come to accept by extrapolation that other people are most likely pretty much like us. And therefore consciousness is a universal property of at least normal humans. But it's very hard to test for. How would you tell an aware human from somebody who has all the same behaviours but has no idea what they're doing? Like most other drivers.
Steve, I know you're under some time pressure, so maybe we should draw a close at this point.
Happy to take one more.
One more question.
How do you define consciousness? Because, I mean, at one level you could sort of say it's a matter of pattern recognition, i.e. people's previous history, plus prediction, projecting the pattern into the future, and then sort of comparing and looking at the errors. I mean, that would be one way, a mechanistic way of looking at consciousness.
Well, but I could build a machine that does that and it wouldn't be conscious.
Yeah, but consciousness, of course, has this sort of variability, doesn't it? The unpredictability.
Well, as I said, I'm not an expert on this, and I think consciousness is very challenging. It's very ill-defined. It's kind of, I think, probably implicit in the Turing test. Okay, so I think Turing probably had this idea that if you engage with these entities for long enough, you can kind of tell if they're aware or if they're not. But whether that's right, I don't know. Whether the Turing test is still the best test for general artificial intelligence, I think, is the subject of some debate. It's lasted a long time, it's had a good innings.
So basically, at the moment, we're really actually grasping at rather nebulous thoughts as to what it might be, and we haven't actually, because it's in such a difficult area, we haven't really nailed it. So it's actually hard to test whether something is or isn't conscious.
Yeah. As I say, it's not an issue that affects our day-to-day research. It's such a long way from where we're currently operating that it isn't a concern. It's just interesting because as humans, philosophically, consciousness is important to us, and so we wonder naturally. But I can't offer any expert opinion on this at all.
Okay, well, there I think we'll leave it. So thank you very much again, Steve, for a very interesting talk. And perhaps you join with me now in thanking Steve again for being
So next week, ask the graphene people when graphene will become conscious.